Hello everyone and welcome to my workshop on exploit analysis. My name is Boris Larin. I'm a security researcher at Kaspersky GReAT. I'm focused on finding zero-day exploits. I do reverse engineering, I develop exploit detections, and do hunting. In the last 3 years, me and my colleagues have discovered more than 11 in the wild zero-day exploits. All of them were used in different malware campaigns. If you like to learn more about these exploits that we found in the past, you can check out my page on securelist.com. In today's workshop, I'm going to teach you how to set up your own debugging lab, how to use Windows debugger, I will show you some useful tricks, and finally, I will demonstrate you how I analyzed the latest zero days that I've discovered, CV 2021-28-310. Ability to analyze exploits is an essential skill in malware analysis and vulnerability research. I think that malware analysts should have a good knowledge about popular exploits and be able to recognize a zero-day when they find one. Malware analysts also should be able to recognize a CV ID if exploit uses known vulnerability. CV ID is a potent threat indicator, so in case if you see that attackers use some known vulnerability in the attacks, be sure to include this information to your blog post or report. On the other hand, vulnerability researchers can analyze the exploit, understand what a root case of this vulnerability, and help to find and fix other similar vulnerabilities. Scenario for today's workshop is that you are a malware analyst and you have discovered an unknown elevation of privilege exploit on virus total. You need to analyze it and find the root case of exploited vulnerability. First thing first, you need to set up your own debugging lab. You need to set up a virtual machine with Windows 10 operating system. Quite handy that Microsoft provides images for different virtual machines. You can get an image with the latest version of Windows 10, and also you can get an images for older versions of Windows with different browsers like Internet Explorer 9 or 10. The next step is to get debugging tools. You can get two different versions of Windows Debugger. There is a WinDBG preview, which is a new, sleek-looking version of Windows Debugger. It has some new features like beta scripting and also time traveler debugger support, and it just looks better. You can get it from Microsoft Store. There is also a classic version of Windows Debugger. It comes with Windows SDK, and today I will be showing you the classic one. Boot your virtual machine. You need to install Windows Debugger on your host and on your guest machines. So press next. Probably don't want to send this information. Accept. You need to install debugging tools for Windows. You need to install application verifier. And well, that's enough. So the next step is to set up your debugging. And many tutorials that I have seen, they teach how to set up debugging over COM port. Don't do this, it's extremely slow. There are better options. First of all, you can set up debugging over network. And there is also a virtual KD. I will show you how to set up this. So in case if you are using VMware, you need to add an additional network adapter, choose a host-only adapter, press OK. Then you need to get an IP address of your host machine for this host-only network. For VMware, it's VMnet1, so this is my IP address. Then go to your guest machine, go to control panel, go to device manager. Here you need to get PCI information for your network adapter. For me, it's PCI bus 27, device 0, function 0. Then open command prompt and do the following command. And also do this additional command. Here you provide that you need network debugging. You provide an address of host machine, debugging port, and also debugging password. Then you need to set up PCI bus parameters for your network card which will be used for debugging. After that, you can restart your guest machine. So now open WinDBG on your host machine and press kernel debugging. Here you provide port number and password for your debugging machine. Wait until it connects. At your first launch, you can see the same picture. Like, it's hard to tell if it actually does something or not, because it says that kernel debugger connection established, but also at status you can see that debugger is not connected, and it kind of doesn't allow to do anything. You just need to wait, because at first launch it tries to download all required symbols. Just wait, yeah, everything is fine. So right now I will show you how to install VirtualKD. Now you go to VirtualKD website and you need to get it. Then you copy it on your guest machine. Go to the target folder and use vm install. So here you press install, but don't restart your machine right now. We need to check something. So there is a bug in VirtualKD, and sometimes it fails to install connection. So to check if it was properly installed, use bcd read debug settings. If debug type is set to local, we need to use one additional command. For VirtualKD to work, you need COM port debugging. When machine boots, press F8 and disable driver signature enforcement. Then open Virtual Machine Monitor if it comes with VirtualKD. If it says that OS is ready, press Run Debugger button. If you do this first time, it also will take some time to download symbols, but then you just press go and you're ready to do some kernel debugging. Right now, let's talk about Windows debugger commands. I'm not going to talk about all of them, there are too many useful commands and extensions, but I need to mention the most essential ones. I believe that some of these commands do not require additional comments. There is a quite useful command X. You can use it to show debug symbols in different modules. The process command, you can use it during kernel mode debugging to display a list of all processes, or get your current process, or find some process you are looking for. There is also process command, which is used for process context switch. WinDBG also supports its own expression language, which is very useful. Here you can see commands that you can use to display memory contents. You can display memory as bytes, double words, quad words. You can display strings. You can display memory pointers with symbols. It's useful when you debug some virtual objects. There is also a very useful command display type. You can use it to display structures if symbols are available. So here you can see some breakpoints related commands. You can get the list of all breakpoints. You can remove some of them. You can set breakpoints. Here I also demonstrate how to set up a conditional breakpoint. You can also set up memory access breakpoints. I need to mention that it's possible to use expressions as command parameters. It's really useful to use this with conditional breakpoints. You can read more about expression language which is used by WinDBG by the following link. Here are some additional comments which will be useful for you. Reload user, you need to use this when you connect to user mode process from kernel mode debugger. fmatch x86, fmatch md64, this is what you need to use to switch your processor mode. And session, this command can be used to display and switch the session contexts. You will need to use this command if you are going to debug Win32k driver, for example. Let me show you why you need this session command. If you're debugging Win32k driver, this might happen. You see that code uses some valid kernel address, but if you try to display memory contents of this address, WinDBG is not able to show it. But at the same time, if you try to perform a step, you see that this address is a valid address, and code was able to read something that was located there. Win32k driver is located in some special address space. So to be able to read this data in WinDBG, you need to switch your current session. You can do it like this. Sometime you might need to set up a user mode breakpoint with kernel mode debugging, and to be sure that your breakpoint will be fired, you need to do the following. So first break into the debugger, switch processor mode if you need this. Then you need to get the address of your process block for your desired process. Then use this address to switch the process context. Then check if process context switched successfully, and only after that set up your breakpoint. Let me demonstrate how to do this. So first I break into the debugger, then I get the process block of my desired process. Let it be the tvm.exe. Here's the address of your process block. So then I use this address to switch to this process. It says that you need to press G for switch to happen. Now use this command to see if process was switched successfully, and it was switched successfully in my case. So right now I will make some breakpoint. I want to set breakpoint on process data function. There are 3 different functions with process data mask in DVM core, and I will set up a breakpoint on one of them. My breakpoint is installed, and we can press run. And my breakpoint is hit. Now when we set up our own debugging lab and we learn how to use WinDBG, we can start with exploit analysis. Exploit root case analysis can work in both ways. You can analyze code path from trigger to crash, or you can first see the crash and then see how it was triggered. I usually start a root case analysis with the reversion of exploit code. My favorite way is to create a small proof of concept. Here are the ways how you can do this. First of all, there is a hex arrays. Then, if code is obfuscated or packed and you are feeling lazy, don't want to deobfuscate it, you can get a trace of executed API calls, system calls, and installed hooks with your sandbox, emulator, debugger, whatever you have, and then convert this trace to C file and compile it. Well, this is my favorite way. This is how I like to do this, but it's not necessary. Well, the thing is that during exploitation, the system runs very unstable. So if you stop exploit at the right time, you can cause a blue screen of death. You can use it to debug your exploit and find the root case. But for this case, I created my small POC, and right now I will try to run it. Well, I see that something happens. We don't see a blue screen of death, but there was black screen for a matter of few seconds. I guess some process crashed. If we will go to Emmet Viewer, we can see that there was a crash. dvm.exe crashed. And also you can see exception code. It's access violation. So from here we can say that this exploit, it exploits vulnerability in dvm.exe process. It's a user mod vulnerability. Because it's a user mod process, we will need to perform a user mod debugging of a system process. You can do this from kernel mod. You will need to open gflags. It's a special utility that you can use to enable different debugging options. You can make your kernel debugger to break on every user level exception. It can cause a lot of noise. You will have to filter all of them. But I believe that for this case, it's better to use remote user mod debugging. For this to work, you need to start a debugging server and then use this command to connect to your debugging server from your host machine. Then choose attach to process and choose the process that you would like to debug. So we choose dvm.exe. So okay, we attached. Right now, let's start our exploit once again. Okay, we see that exception happened. So let's check call stack. Here we can see that exception happened in function channel delete resource that was executed from process message function. It looks quite interesting. So I guess exploits send some messages which then triggers this exception. We can see what data is located here. We can see that proof of concept manages to write some object and it causes access violation. Okay, let's do this once again. Okay, well, dvm.exe restarts itself. It's quite handy. Let's attach again. And start exploit one more time. We can see that this time access violation happens in another function. And let's repeat this process once again. Press run and launch exploit. Okay, so this time it's another function. So you see that each time we run our exploit, crash happens in different functions. So how to find the real root case? Because we only see crashes after exploit works. So let's do something new. Let's enable full heap verification for dvm.exe process. Okay, page heap enabled. Right now we need to crash the VM process one more time. For heap verification to work, we need to restart the VM process. So for restarting, we will just crash it one more time. And next time it restarts, heap verification will be enabled. Okay, let's see what happens this time. Attach to the process. Press run and launch exploit again. Okay, something new happens. We see that this time we have a second chance exception. It means that exception handler of the VM process was executed. There is a special mil instrumentation handle failure instruction, and it was executed from C property set process set property value function, which was executed from process message, process command batch. Okay, it's quite interesting. Let's execute it again. Maybe something else happens. Okay, so we attach to the process and press run. Start exploit again. And okay, so it's the same exception right at the same place. It looks like with heap verification, exception happens always at the same place. So let's check what this code looks like. It's time to open IDA. Okay, here's the process set property value. And here is when fail fast is executed. There are two code paths leading to this block. Let's figure out which one of them is used. We need to set a breakpoint for before fail fast function is executed. So let's check it. Okay, I see that well, R6 is equal to C0, C0. Okay, I recognize this value in RBX register. This basic block is executed. So what happens before it? Okay, so this check happens. So this value is compared to something like it here. It looks like some count or ID. And in our case, R6 is equal to value read from undefined memory. It's quite interesting. Okay, so let's set one more breakpoint for this basic block. Attach to the process one more time. Okay, we set this new breakpoint. And run exploit. Okay, our breakpoint is hit. Let's dump values of some registers, R8. So I believe this is command that was somehow sent to DVM process from my proof of concept. Okay, and R9 points to value that gets written. So R8 is our command. I believe that we have full control on the things that it gets compared. ES6, it's somehow read from this table. It's interesting because you can see that ES6 value was not initialized. So before we continue with DVM core, let me show you the code that I have inside my proof of concept. Exploit uses just 3 syscalls from Win32k. These syscalls are related to direct composition API. They are used to send some buffer with commands. Here you can see how these commands are created. They basically just written one after another. Looks like first word means some command ID, and then there comes command parameters. Each command has its own parameters. Let's try to figure out what these commands do and what parameters are. This is a function that processes buffer with commands. Process command buffer. That this function has a really big switch statement. There are 21 cases. Our commands should be handled here. Okay, so let's look for the command with ID 1. Okay, what it does. So for first case, it will execute function create resource. We can say that command id1 means create resource. Command 3. id3 means release resource. And then we also have id12. Let's look for it. So it's another function, so it was not found. Let's look, maybe it handled preload to the switch. Okay, it's here. Okay, here's some logic. Something else gets compared. And here it calls setBufferProperty function. Command id12 means setBufferProperty. Now we can rename these IDs in our code. So the first command is create resource. Second command is release resource. And our third command is setBufferProperty. I spent a few minutes on reverse engineering, and I was able to get the names for all command IDs. Here they are. Right now we can rename our commands. This command create resource, command release resource, and command setBufferProperty. You see that these command IDs do not match the ones that we have in our dump. So let's look for this ID. I believe it should be somewhere in code. Okay. And we have a number of functions found. Okay, so here we have property set vector 3, property set vector 2, property set matrix. I believe that's where command sent to the kernel gets converted to the VM core command. Okay, so what we have here. It's good to have symbols. Here, third parameter is decomposition expressed type. So in our case, expression type is equal to 23. So what happens before this function? Get resource function. Its third parameter is mil resource type. What else do we have? For our function, it's a case 394, which is what we have seen in our dump. And it gets written here. So I guess was correct. Okay, we have seen this ID here, get resource type. So I guess this parameter means resource type. And here comes, well, it should be some integer. I believe it's a resource ID, so we can rename it. So the first parameter is resource ID, then comes resource type and some flag. We can assume that for all commands, first parameter is resource ID. Probably it's some another ID that gets compared, and it gets read from this subset in that command. In our case, it's 23. And then, depending on this value, different logic will be called. So here it's float, property set for float. Here we have vector 2. It's our case. Okay, another case. This time it's vector 3. So it looks like expression type equal to 23 means vector 2. And it gets written here. Okay. We can say that it's vector 2. Okay, what other parameters are? Well, this looks like some ID because it multiplied at 8 and then it's used to get some data from the table. And then data that gets read compared to this value. So this is resource ID, this is some other ID, and this is the value that gets compared. What we have next? As you remember, 9 points to value that gets written. So it gets here from our command offset 18. So it's here. So this quad word is the value that gets written. We can rename it. What else do we have? So this is some ID. It's also used in this function. Here it's also used as ID. There are some another data gets compared. Okay, so it makes sense. Because this function is called setProperty, I believe it's a property ID for a resource. Each resource should have a number of different properties, and it's possible to set or update them. We checked what this parameter looks like in command, so maybe it's some offset for data, for property data. So let's change names. It's property ID. And this is property data offset. I will call it storage offset. So we have the last unknown parameter, and it gets compared here. It's a flag. Depending on this flag, it would call add property or update property functions. Okay, so it was the last unknown parameter. You can say that it's update flag. We know all the commands and we know all the parameters. What the root case of exploit is? It looks like this code doesn't check if provided property ID is a less than count of all properties assigned to resource. Here happens out of boundary access, and retrieve data is used for this comparison. For this check to pass, data after buffer should be equal to data offset that we provide. Then update property function gets executed. Here additional check happens. There should be expression type written to the memory after buffer. And then it uses our provided property ID to write our value past another buffer. And these two checks, they could be bypassed if exploit manages to spray the memory at the right locations. We were able to find the root case for this exploit, and that's all for our workshop. Thank you for coming. If you want to read the full write-up about this exploit, you can do it by the following link.